on the recording. So I'm turning on the recording. Okay, so we are. Did I get turned on? So we are officially started. Yeah, it's on. Okay, let's see. So does everyone have their name tag? I see one person. You ever made a name tag? Okay, all right. Well, it's very easy. So it's actually a name tag. All right, so I'm back at the front here temporarily. I'm going to give people some graph paper in the usual style for people online. So hang on for a minute. I'll be back. So if you don't feel like you need any. Okay. Got leftovers. How much? Right. I know there's just at least one. All right. Okay, I'm back up here. Somebody remind me to pass out the roll in a few minutes here. And we'll go in.
Yes. Okay.
For those people that haven't been here to sign the roll, your name, I have put your name if you've attended online, which I think everybody has. So just look at the previous sheet or maybe the sheet before that, okay, to find your name where I put you, and then you just sign in that slot, okay? When this comes down. So someone remind me in a few minutes here, once we think everyone has come in to pass that around, okay? See where we are. Fine here. Okay, looking good. Let me see if I can switch to the notes. Oh, but I guess before I do that, let me mention the homework. So we do have a homework due tonight, right? Okay. On this entering answer. So there's no real content here, right? This is just about how you use the WebAssign system, right? Okay. And you may have some questions about it though, because some of the widgets in WebAssign are, you have to get used to using them right. In one particular, the graphing widgets, or maybe using that math palette where you can enter, math notation, that might sometimes cause you issues. But the graphing widgets, which we really won't be using that much in the class anyway, but maybe sometimes, those are the ones that maybe can be a little bit tricky sometimes until you practice with them. But anyway, do y'all have any questions about this assignment? You have to help me because I don't use the widgets that frequently either. Okay, so sometimes I don't see them except at the beginning of each semester, and then so I forget about using them as well. No questions. I've had a couple questions sent to me, not necessarily about this homework, but Sonny, did you see my response to your question? Oh, okay. Well, I did respond to your question. So yeah, you have the equation slightly wrong. So you need to go back and look at it's partially correct, but it's a little incorrect. So you need to go back and see if you can fix that. Okay. I think I put the right equation in there so you can figure out why the right equation is correct. Unless WebAssign has a mistake in it. Okay. So no questions about this. I'm going to trust your judgment on that. Okay. Sometimes I will open homeworks and mention specific problems that I know people are having difficulty with, even if you don't ask me questions about them. But on this one, since there's really no math content here, I'm going to assume that you guys can finish that one. So make sure it's you do it by midnight, right? But remember that if you do run over, right, you can request an automatic extension, and I don't have to approve that, so you can just request that. You have to do it like the next day, however, after the due date, right? Request the automatic extension. Be sure you do it like within a day, because there's a time limit on how long you have to request the extension. And make sure you request the automatic extension by following these instructions so that I don't have to approve it, okay? It will just happen automatically. Now, if you get an extension, though, remember you do get some penalty, right? Okay, but it's on the points earned after the extension, not the points earned before the extension. But if you forgot what I was going to say. But yeah, but it's better to have, even the points with the penalty than to have no points at all. So keep working on your homework, right? Okay, try to keep working on your homework even after the due date. Just be sure to request the extension in time. But Amanda, your situation is slightly different, so you should email me a extension request. Okay. Yeah, right. Because so that I can approve that. Okay. All right. So much for that message. So you see what homework is coming up, right? There's one on the coordinate plane. So we're just about finished talking about this section. So you'll be able to finish this homework after today for sure. Well, after the first few minutes here for sure. And so that's not due till next Monday, right? Remember, the grace period ends on Wednesday, though. So if you're not going to actually purchase the access to the homework by Wednesday, then try to finish this before Wednesday. So that will give you a little bit of extra time, right? Okay, to purchase. You don't, you won't lose any of your grade, right, if you run past the that grace period. It'll just block you from working on or homeworks. Yeah.
Every previous videos I wasn't sure what's happening.
Yeah, it's on 1.9.
Okay.
Yeah, but we don't really follow the book that closely, so you can look at the syllabus and see the sections that we're at, but I really don't refer to the sections that in class that much. They're in the homework, they're listed in the homework, but I don't explicitly refer to them in class. We really don't use material from the textbook that much. It's mostly what's in my notes. In fact, it's almost entirely what's in the notes. Okay. All right. So there we are with the homework. So I'm not going to say any more about that, except remember the optional extra credit, you get flux dollars for that. So not due until the time of the test. Work on that at your leisure. So as long as you have 80% done by the time of the test, you'll get the 10 flux dollars, right? Okay. Added to your flux dollar total. Okay, let me switch to the notes. Any questions from the Zoom class? Anyone chatting at me there? I'm not good about keeping up with the chat. Oh, I have some recall practice for you. Oh, I forgot. Okay, so people at home, right? Okay, alert, red alert. All right. We have just a little bit of recall practice on what we were doing last time. So just see if you can recall what we were talking about at the end of class last time. If you can't recall it, that's fine. Just try to recall as best you can. It's just the act of trying to recall that's important here. You don't get it completely correct, then of course it'd be better if you got it correct. But if you don't get it completely correct, that's fine. It's just try to force yourself, however, to remember. Okay, that's what recall practice is. So what I want you to try to do here is, this is actually graphing, so you will need the graphing paper here. I actually want you to try to graph this equation, right? Okay, using your knowledge of what the graph should look like. So you're not going to be, making a table of points, right, and plotting points, correct, right? Okay, you should have some prior knowledge of what that graph of that equation should look like, right? Okay, so that you can construct the graph really quickly. All right, so try to remember, what sort of curve am I going to get from this equation when I graph the solutions to this equation, right? What sort of curve am I going to get first, right? And then once you remember the curve, oh yeah, how from that equation can I find the details of the curve, right? So it will be the important features of the curve, right? So it will be easy for me to graph, right? So I don't have to, try to plot a bunch of points and connect them with a smooth curve. That's going to be too clumsy for this. This equation is too complicated for that naive approach to graphing. Right now? Oh yeah, no, I'm not. Oh, I'm glad you saw that. I almost screwed up the whole thing. That would give us a completely different sort of curve. And yeah, there's supposed to be a plus there. Sorry. Okay, right. If we are subtracting there, we do get an interesting curve, but it's not the one I care about at the moment. Okay, all right. Okay. So I'm just going to walk around and observe, right? And stop you on the hand if something wrong. On side so all right. And so you together. No, all that is where All right. Well, most people got that, so that was pretty good. Okay. And then,
I remember this, I just got some.
this is a little bit simple.
Okay.
Yeah, right. Okay. I know what you're trying to do there. Right?
Yeah.
It's not necessary. Okay, in this problem. All right. So, all right. So, a lot of people did well on that. Okay, and some people forgot a few of the. Some people forgot a few of the details. Okay, and here's the real detail that you want to remember. Okay, this is going to be the equation for a circle. Okay, so if you have an equation that looks like in this form, does have to be a plus there though. If it looks like it's in this form, then that equation is going to be the equation for a circle. So when you graph that equation, you're going to get a circle. Okay. Now, of course, there are lots of different circles, right? So we have to know more information about the circle in order to make the graph efficiently. We don't want to have to plot any points, right? Or not many points anyway. And so it's easy to graph a circle, however, if you know the center of the circle and you know the radius of the circle, right? That makes it easy to draw the graph. But that information comes right out of this equation. Okay, the center of the circle is going to be these two, or I should say the coordinates for the center of the circle are going to be these two numbers, right? The numbers that are subtracted from x and y in the equation. So the center is HK and the radius is going to be R. Okay, so the square root of this constant on the right hand side, that's going to be your the radius of your circle. So in this particular equation, right, in this particular equation, let's see, what is the center going to be? We can almost read that off of the equation, correct? So what did y'all get as the center? Yeah, -5 and +2, right? Okay. Remember, in this equation, these constants are subtracted from x and y. So 2 is subtracted from y, so you know that the y coordinate center is just 2. But here, since you have x plus 5, you have to write this as a subtraction to make it fit this form. So this is x. X plus 5 is the same as x minus a -5. So the x coordinate of the center is -5, not 5. All right, did y'all get that at home? Okay, there's the center is -5 and 2. And then what's the radius then? It's 5, right? Because you just take the square root of the 25. Remember, on the right-hand side of this equation, you have the radius squared. So the radius is the square root of the number that's on the right-hand side. Fortunately, 25 is a perfect square. So it's easy to compute its square root. So square root of 25 is just 5. So that's what this circle looks like. Okay, or that's what the graph of this equation looks like. It turns out to be a circle, and there's the center, and there's the center, and there is the radius. So you can sketch a graph of that really quickly, right? You got to draw some axes here. And then just plot that center, which is at -5 and 2, right? And then I didn't leave myself enough room. Okay. And then the radius is 5. So so you can easily plot some points here on the edge of the circle. If I had left myself enough room, I could have plotted some points on the edge of the circle. We're missing that point on the left hand side. Okay, and then just connect those with a circle, right? So you're going to get a circle that looks something like this, but got this side cut off. Okay, All right, so there's a really ugly graph of that circle. Okay. Some other sort of curve. Did you get your name tag? Have you made a name tag? Yeah. Let's go grab it. It's over there. Okay. All right. Okay, so there's our recall practice. Hope that helped y'all recall some things that you learned last time. Okay. We're going to need that knowledge again. So let me scroll up here because we're not quite finished with the notes. Here's one that I'm going to have y'all work on in just a second, but not yet. So don't start on that one. Don't try to start on that one yet. Okay. I'm still going to show you one more example of this process called completing the square, because sometimes we're given the graph of a circle, equation for a circle, and we're asked to graph it, or, we're asked something about the circle, but the equation is not in standard form. The standard form was the form I just showed you. X minus h squared plus y minus k squared equal r squared. That's called standard form. And that's very easy when the equation is written in that form, right? It's very easy to, know everything there is to know about that circle. But many times you'll be given an equation that happens to be the equation for a circle, but it's not written in standard form. And then it's much harder, to understand what the circle looks like. Okay. So let's see an example of that. We saw one example at the end of class last time, but let me show you another example, and just to remind you of this process. Then I'll let y'all try one. Okay, you really do need to practice this, and it is in that next homework that's due, the 1.9 homework, and that's probably the hardest part, maybe, of that homework assignment. Okay, so this problem says show the equation x squared plus y squared minus 4x plus 10y minus 20 showed equals 0. All that's equal to 0. Showed that is in fact a circle. So that really is the equation for a circle. And then what's the center and the radius? Okay. So that would be easy to graph. We're not going to actually graph it, but once we know the center and the radius, right, then it's pretty easy to graph the circle, correct? Okay. So we have to take this equation, which is in simplified form, what I would call simplified form, and we want to write it back in that x minus h squared plus y minus k squared equal r squared form. That's called standard form, or sometimes I call that factored form. All right. Because to me, that's a little bit more descriptive what that form of the equation looks like. Okay. But I call this simplified form because all of the arithmetic that can be done by hand in this equation has been done. Okay, so there's no more arithmetic you could carry out by hand in this equation. There's no like terms to add together, right? You can't add anything together. You can't square the x's and the y's because you don't know what x and y are equal to, right? So you can't carry out that squaring, right? So by hand, this is it, right? You can't really do any of the arithmetic or algebra that's left in this equation. So I call that simplified form. But we're going to put this into this form, standard form or factored form, right? And then we'll know everything there is to know about the circle. All right, so that process that we're going to use is called completing the square. All right, and so and that's a very useful process that we use a lot in algebra in different situations, not only just this situation, because it's very often useful to have expressions written in the form of a perfect square. There are other situations where that's useful. But let me show you how we're going to use completing the square on this particular equation. All right, so the first thing I want to do here now, so the first step, now I don't have these steps written down one by one, so you need to kind of pay attention to what I'm saying here, but you in your notes, you may want to describe these step by step. What should I say here? Process, right? And the first step in that process is to gather your x terms together. So this is an x term, and this is also an x term. So I want to put those side by side. okay, like this. And the y terms, I also want to put those side by side. Now, notice when I'm doing, so there's a y squared, it is a 10y, right? So I'm going to put that, those two terms together. And did I get the signs right? I think so. And then this minus 20, this constant, let's move that back over to the right-hand side, okay? Because remember, in standard form, you want a constant, this r is a constant, x and y are the variables here, r is a constant. So you want that on the right-hand side, a constant on the right-hand side, ultimate anyway. So let's take that minus 20 and let's move it over to the right-hand side. Now, notice I'm leaving a little bit of, I didn't really leave enough, but I was trying to leave a little bit of space there around the x's and the y's, because I'm going to group those terms together. Let me leave myself a little bit of room here after the 10y or the equals 20. So I want to group these terms together. So I'm going to group them in parentheses like this, because what I would like to be able to do is factor the expressions in the parentheses. So I'd like to be able to factor x squared minus 4x, and I would like to be able to factor y squared plus 10y. Now, as we discussed last time, you can factor x squared minus 4x already. That does factor, but the way you factor it is factoring out an x, right? And you would get x times x minus 4, which is not, although that is factored, that's not quite the factorization I'm looking for. I want to be able to factor the x squared minus 4x so that it will factor as a perfect square, okay? X times x minus 4 is not a perfect square, because x and x minus 4 are not the same thing, right? Okay. Remember, a perfect square is when you multiply a quantity by itself, right? Or an expression by itself. So this is not the same thing multiplied together. So this is not a perfect square. So make a long story short here, I've gone off track here in doing this factoring. So so let's erase that. That's not useful. And the same thing happens here. You can factor a y out of these two terms, but you won't get this factored as a perfect square. So to make it factor as a perfect square, I'm going to have to cheat a little bit. So what I'm going to do is insert a number here inside the parentheses. So that's kind of cheating, so that I can get it to factor as a perfect square. All right. So I get it to factor the way I want it. Now, you do not remember, you do not have to guess at the number you want to put in parentheses. Okay. Do not have to just try to figure that out on your own. Okay. What you do is take the coefficient of x, divide that by 2 and square it. And that will be the number that you know you want to add into the parentheses. So that is 4, right? Because minus 4 divided by 2 is negative 2 squared is positive 4, right? So I'm going to put a positive 4 in here. And I'm going to do the same thing with the parentheses that have the y's, all right? So take the 10, divide that by 2 and square it. So you get, of course, 5 squared there, which is 25. So in here, you add in a 25. Now, I have definitely cheated because I changed the equation. I put a 4 and a 25, right? Okay, on the left-hand side of the equation. So it's not the same equation anymore. So that's cheating. But so I have to undo my cheating. And the way I undo the cheating is just add the same numbers to the right-hand side. I want to keep the equation balanced, right? So just on the right-hand side, also add in a 4 and a 25. So you have not unbalanced this equation, okay? What now? No, well, okay, so Emil, you could think of it 2 ways, all right? You could think of, since I added these on the right-hand side, I will also subtract them on the right-hand side. I'm sorry, on the left-hand side. So let me say that again. Since I added 4 and 25 on the left-hand side, I can think of subtracting also on the left-hand side. So that would be 4 minus 4 is 0 and 25 minus 25 is 0, right? So I wouldn't have really done any damage, correct? But now, when you take those over to the right-hand side, the -4 and the -25, what happens? They become plus or plus 25, which is exactly what I wrote, correct? Okay. So either way, you either how you want to think of it, subtracting from the left-hand side or adding to the right-hand side is the same.
I don't know. Used to play like back then.
Oh, if you add here, you subtract here. No, no. You'll make the equation even more unbalanced. If you add on this side, you have to add on this side. Or if you subtract on this side, you have to subtract on this side. So you're misremembering what. Okay. All right. So now we're here. Well, now we're going to actually do the factoring. So we should be in great shape for factoring. I can also add these constants on the right-hand side, correct? So that's 24 plus 25, which I believe is 49, correct? How convenient. That's a perfect square. So we got lucky there. And now let's factor the x squared minus 4x plus 4. And that, I told you, will factor as a perfect square. So you're guaranteed that's going to factor as a perfect square. So it's going to be x, and then the number you'll put after the x is going to be whatever you squared over here. I forgot to write -2 squared there. So you just put in x minus 2. Let's put the -2 right. Remember, we squared the -2 to get the 4. So I'm going to put the -2 right here. Don't forget you put the square here. You can check this now if you don't believe it. Take x minus 2 and square it, and you will get x squared minus 4x plus 4. Okay. Be sure you square that properly, however, right? To get x squared minus 4x plus 4. So these two things are the same. And now you know this factors as y, and then what's the second number? Yeah, the 5, right? It's plus 5, right? So you have y plus 5 squared. You're done.
So I understood I didn't have the 5%.
Okay, because I added them to this side, right? I put plus 4 and plus 25, right? Yeah.
Okay.
So if I add them to the left-hand side to keep the equation balanced, I also have to add them to the right-hand side. Think of a scale. Add a pound to the left-hand side of the scale. You're going to have to add a pound to the right-hand side of the scale also to keep the scale balanced, correct? Yeah. If you subtract from one side of the scale, you have to subtract from the other side to keep them balanced as well, right? Yeah. So just think of it as balancing things. Okay, well, now we're done, right? We know everything about this circle. What is so this is really the recall practice that you just did. What's the center here? What's the x coordinate of the center? +2, right? And what is -5? Okay. And the radius is easy. That is what? 7, right? Square root of 49. If this number doesn't turn out to be a perfect square, that's okay. You still have to take its square root to get the radius. So if that were 40 instead of 49, your radius would be the square root of 40. Square root of 40 is not a perfect square. So, if you want to draw that, you would have to get your calculator to estimate square root of 40, but still take the square root of the right-hand side to get the radius. Okay. All right. So you think you can do that, guys at home? You think you can do that? Okay. Emil says no. All right. Okay. Well, we're going to find out. All right. So let's try one for you guys to do. All right. So let's try this one. Unfortunately, I can't show all of the previous steps on the screen at the same time. So I hope you wrote those down or you remembered them. Okay. So show that this equation also is a circle and find for me the center and the radius. So remember, you're going to take this equation and you're going to put it into this form, standard form, right? Standard or factored form. Okay, guys at home, so can y'all do that? Start the steps there, right? Okay, of of doing this and see if you can get to factored form. All right, so I'm going to go around the class and I'm going to of the people in the class, I'm going to talk to them while they're doing them. Okay, I will stop also here up at the podium. So if you guys that on Zoom have questions, then you can chat them in, or if you see me again, I don't know if you'll ever be able to see me again, but I'll come back and ask questions here also while we're doing this. Okay, so now you guys at home take this seriously, because I'm probably going to ask for someone at home to help me with the answer at the end. Okay, because I'm going to see what the people in the class are doing, so I'll know what they have done. But I'll have to ask you guys at home what you have done, so I can see what your issues are. Okay, all right. Okay, I'm also starting to roll sheet, so we're going to sign, look back on the previous find the page, find the past. Okay, people at home, do y'all have questions? Any questions there? Not hearing any, so.
I don't know if it's still the- I was in, talking.
Okay,
It's happening.
well, I did hear people earlier,
Yeah.
so, but they can chat also. with me. Okay, I think everyone in the class got that, okay, that I got around to looking at. All right, so so let's ask someone at home, okay, if you can tell us what this equation looks like in standard form, right, in factored form, so you can read that all for us. Who wants to share that? Who's at the house or wherever you're at? Not sure you're at the house, okay. Wherever you're at in Zoom world. Who wants to share with us? You'll have to unmute yourself so you can talk to us.
I got,
Is it Pooja?
this is Pooja.
Ah, hi Pooja. Yes.
I got x plus 4 squared plus y minus 6 squared equals 49.
So x plus 4 squared. Does that sound right, folks? Plus, and then what, Pooja?
Y minus 6 squared
Y minus 6 squared. Does that look right?
equals 49.
Equals 49. Yeah. Okay. One of the more common mistakes, was really the easiest part of the problem was adding constants on the right hand side, and some people were adding those wrong, but it's supposed to add up to 49 eventually, right? You're right, Pusha. Okay, so Pusha, there, what then is, if we wanted to graph this, that's really not the instruction, but if we wanted to graph it, where would we put the center of the circle?
-4 and 6.
Perfect. Yeah, -4 and +6, right, for the center. And then how much radius would we use there in our graph? So what's our radius?
7.
7. Perfect. Great, Pooja. Yeah, that's right. Okay. All right. So, oh, Hannah, you got 7.41. So you were off a little bit there on your radius. Did you think the radius was 55?
Yes, I
Hannah?
did. Mistake.
Okay, yeah, because I think here's what, Hannah, here's what probably happened. When you move this to this side, the -3 over here, you want to change the +3 that's on the left hand side. When you move that to the right hand side, you want to make it -3. Did you do that?
No, I did not.
Yeah, so then you ended up a little bit off there. Okay. Instead, so yeah, so the actual radius, I mean, the actual constant on the right hand side turns out to be 49. So the radius is square root of 7. Who else there answered for us? Is that Kevin? There we go. Kenneth. Kenneth, what's your last name? Kenneth, what's your last name? You can chat it in too if you want to. Just wanted to know exactly who I was talking to there. Okay, all right, so excellent. Y'all did that pretty good. Okay, if you can do that, that will be on the test for sure, the first test. So of course it's going to be on the homework as well. So if you can do that, then you can carry that process out confidently, and that's gonna that bodes well for the first test. Okay, because that's going to earn you some points there for sure on the first test. Yeah.
I think.
Yeah. Yeah, that's the easy way of figuring out how to create a perfect square, right? When we're going through this process, completing the square. Yeah, which sometimes which comes up in other situations as well. yeah, there are other opportunities for completing the square. Okay, not just in writing down equations for circles, but other situations as well. All right, so let's switch. I'm going to now. So we're done with our circles notes, and so I'm going to switch now, and we're going to talk about another type of curve, but very closely related to a circle. Ellipse. Yeah. Okay. It's an ellipse. Yeah. All right. So ellipse is now very similar to circles. Now, don't forget but they're not straight lines. But don't forget we're still coming back to talk about straight lines. Okay, which is a simpler type of curve and more useful than circles and ellipses. Although both circles and ellipses, of course, have important applications, right? But nothing so important as straight lines. But we're coming back to straight lines, and we'll talk about starting on Wednesday, because we have to talk about that in much greater detail than we do circles and ellipses. Okay. All right. So we just talked about, right, that if you have a circle with a center of 0, 0, so kind of a simple circle located its center at the origin, and the radiuses are right, then the equation for that circle is going to look like this, right? X minus the x coordinate of the origin, which is 0 squared, plus y minus the y coordinate of the origin, which is also 0 squared, right, equal to your radius squared. Of course, since this is just x minus 0, you can just write that as x. So this first term simplifies to just x squared, and the y minus 0 just simplifies to y squared, right? So for circles that are centered at the origin, whose center is 0, 0, their equations simplify very nicely, right, to a very simple equation, just x squared plus y squared equal to a constant squared, right, the radius squared. Now, I want you to notice here that in the equation for a circle centered at the origin, the coefficient for the x squared and the y squared is 1 in both cases, right? You have 1x squared plus 1y squared. But if you start varying those coefficients a little bit, then you will get a different type of curve, all right? So I'm going to show you this equation that looks very similar to the equation for a circle centered at the origin, but it's not, okay? Because notice here, I changed these coefficients slightly from 1. So I made this coefficient 4 just for no good reason other than just as an example here, and I made this coefficient 9, right? And then still have this constant on the right-hand side. So that is also the equation. When you graph it, you're going to get a curve, of course. And the curve you will get here is very similar to a circle, but not quite a circle. All right. So you're going to get an elongated circle called an ellipse. All right. So an ellipse is a circle that kind of you've grabbed on two sides and kind of stretched out, or maybe you grabbed it at the top and the bottom and pulled it up like this. Okay. It's just an elongated circle. All right. So not quite a perfect circle. Now, this ellipse, however, is centered. It does have a center, and the center is going to be the origin. Okay, the center is going to be the origin. But notice that the radius of an ellipse is not steady, right? It's not constant. So if you go in this direction from the center, the radius looks like that's 3, right? Okay, so it's the radius is 3 going if you go straight to the right or straight to the left, right, from the center. This is 3 on the x-axis, and this is -3 on the x-axis. But if you go straight up, you don't go distance 3, you only go distance 2, right? Okay, so so of course not a circle. So we're going to talk now about this type of curve, the ellipse, but we're only going to look at ellipses that are centered at the origin. So we're not going to talk about ellipses that are translated or shifted around on the coordinate system. You can have ellipses with different centers than the origin, but we're just going to concentrate here on ellipses that are centered at 0, 0. So all of our ellipses that we deal with in this class will be centered at origin, okay? Unlike circles where we can have centered anywhere. Ellipses now have important applications. They're not just, I'm not just showing you ellipse just as a variation of circles. Ellipses have important applications. For instance, the orbits of the planets around the sun, or in fact, anytime an object is orbiting around another object in space, the orbit of that object will be an ellipse, okay? It's not going to be a circle, okay? So for instance, the orbits of the planets around the sun, they are elliptical, okay? You can't really see it demonstrated in that picture, but orbits of planets are ellipses, okay? This was a tremendous discovery in astronomy, okay, around the time of, in the 1600s, and this is Kepler, who's the Polish astronomer. That's his great, or one of his great discoveries, and this solved a tremendous mystery. It was known that it was known prior to Kepler. In the 1600s, it was known in the 1500s that the orbits of planets were, including the Earth around the sun, were they were thought to be circular. So it was known that the Earth orbited around the sun. Okay, all right, and it was known that the moon orbited around the Earth. Right? Okay, that had already been discovered by Copernicus earlier, and but Copernicus assumed that, and you know, Copernicus got into a lot of trouble with this discovery. This contradicted the teachings of the Catholic Church. So Copernicus, you know, got in trouble for this. And in fact, Copernicus sat on his knowledge of this until he was dead. He didn't publish it until after he was dead because he knew he was going to get in trouble. But Copernicus assumed that these orbits were circular. Okay, he thought they were circular orbits. And so they tried to make predictions about the motion of the planets and the Earth, right? Okay, based on circular orbits, but the predictions were always coming out wrong. Okay, so of course this caused great distress, right? Okay, so if we know these orbits are circular, why can we not predict, you know, where the planets are going to be located in the sky at particular times? But Kepler was the one who realized, based on a very meticulous observations from another astronomer, Kepler realized, oh, these orbits are not in fact circles; these orbits are ellipses. Okay, so so Copernicus was one who was able to undo this mystery of orbits of planets, right? Ellipses have an interesting geometric construction. We're going to talk about their equations, but ellipses also have a geometric construction as well that's kind of fun. If you take a piece of corkboard, for instance, so imagine a flat piece of corkboard, all right, and you place two thumbtacks into the corkboard, all right, okay, and attach a string to the both thumbtacks, okay, and then pull the string tight with a pencil, and then trace out a curve, right? But you got to keep the string pulled tight, okay? That curve that you trace will be an ellipse, all right? So, and if you, of course, if you put the thumbtacks at different locations, right, either further or closer together, you'll get a different ellipse. Or if you make the string longer, right, you'll get a different ellipse. Okay, you can imagine what's going to happen as you bring the two thumbtacks closer together, right? As you bring them closer together, your ellipse is going to become more like what? A circle, right? In fact, if the thumbtacks were in exactly the same position, right? Okay, so if you just really had one thumbtack, then you would get, when you trace out the curve, you would get exactly a circle, right? So if the thumbtacks are closer together, you get a more circular curve. If they're further apart, you get a more elongated curve, right? Okay, in your picture. There's kind of an example of that. So here, if the thumbtacks are kind of far apart, you get a more elongated curve, right? But if you bring the thumbtacks closer together, the shape you'll get is more circular. The locations of these thumbtacks, these are called the focal points. The focal points of the ellipse. Okay, the plural of that is foci. Right? It's not, but sometimes you just say focal points because it's hard to say the word foci sometimes, right? So these thumbtacks are called the foci of the ellipse, but they're not the center of the ellipse. Okay, the center is what you think it is, right? It's right in the middle. It's right in the middle of the ellipse, right? Okay. So when we're dealing with ellipses, we have important points on the ellipse besides the center. Okay, the location of these two focal points is also important to us in understanding the ellipse. All right, now that's kind of the geometric construction of the ellipse. Let me show you. Let me show you the algebraic version of the ellipse. And it looks complicated at first, but it's not. So don't get intimidated by the expressions that you see here. Oh, by the way, I wanted to point out the orbits of the planets. Okay, as I mentioned, those are ellipses, right? But the sun is not at the center of the ellipse. The sun is at one of the focal points of the ellipse. Okay, so if you thought of this as being, for instance, the orbit of the Earth around the sun, then the sun would be at one of the focal points, right? Okay, so you'll notice that at certain times of the year, as the Earth is orbiting around the sun, sometimes the Earth is slightly closer to the sun, but at other times the Earth is further away from the sun. Okay, that is not what causes the seasons, however. Okay? That's not what causes the seasons, because the orbit of the Earth is very nearly circular, right? It's very nearly circular. It's just not quite circular. Okay. In the orbit of the Earth, these two focal points are very close together, very, very close together. Okay. Right. And close to this center, right? Okay. But not quite the same as the center, because then you would have a circle, right? So the orbit of the Earth is very, very close to being a circle, right? Very, very close to being a circle, but not quite. All right. So let me show you now about equations for ellipses. All right. So when we write an equation for ellipse, this is always an ellipse that's centered at the origin. Okay. So the center of the ellipse is going to be at 0, 0. Okay. We're going to get an equation that looks like this. All right. This is called in standard form. So you have just x squared divided by, notice you have a constant squared, plus y squared divided by a constant squared. And on the right-hand side here, we're always going to have 1. We're always going to have 1 because ellipses do not have a radius, right? Okay. Ellipses don't have a radius because the distance from the center of the ellipse is not the same at every point on an ellipse, right? Okay. Some points on the ellipse are closer to the center than others. So you don't have the concept of radius for an ellipse, right? So we'll have an equation that looks like this. Now, you may say, but why do I have two different versions of this equation? Why isn't one version of this equation enough? Why do I have both of these equations written down? Because they appear to be almost the same. Notice, right? Except we've just switched the position of the A and B here in the bottom. Well, let me explain what the difference is. Okay, we're always going to assume in this equation that the A value is larger than the B value. All right, we're going to assume that the A value is larger than value. So if the larger value is beneath the x squared, you're going to get an ellipse that's elongated along the x-axis. Okay, it's elongated along the x-axis. So you'll get an ellipse that is horizontally longer, right, than it is vertically tall, okay? That's if the larger constant is below the x squared. Remember, this constant is always 1. This doesn't change, right? So notice there, we always assume that A is greater than B. And of course, these numbers cannot be 0 because then this equation doesn't make sense, right? This line that runs from the left side of the ellipse to the right side of the ellipse through the center, this is called the major axis of the ellipse. So this horizontal line is called the major axis. And the x-intercepts of the ellipse, where the ellipse crosses the x-axis, they are going to be at -a on the left-hand side of the center and +a on the right-hand side of the center. So the square root of this number, right, okay, that tells you where the ellipse is going to cross the x-axis, right? Okay, it's going to be at -a and +a. Of course, the length of this line segment, right, the length of the major axis is going to be twice a, right? A plus a. So that's why in the notes here it says, oh, the major axis, its horizontal length is twice a. Okay, that's just kind of clear from the picture, right? This vertical axis then is called the minor axis, right? And it starts at -b. So notice the number underneath that squared underneath the y squared, right? It starts at -b and goes up to +b. So the y-intercepts of your ellipse are going to be where it's going to cross the y-axis are -b and +b. These 2 points here, -a and a, the endpoints of the major axis, those are called the vertices of the ellipse, or one, that's plural. So one individual point is called the vertex of the ellipse. Ellipses only have 2 vertices. They do not have 4 vertices. This is not a vertex and this is not a vertex. Okay. I don't know why, but they're not considered vertices, right? Historically, just this point and this point, the ends of the major axis are called the vertices of the ellipse. Now, what if you flip the situation? So what if the larger number is beneath the y squared and the smaller number is beneath the x squared, right? Remember, we always assume that the larger number is a squared, the smaller number is b squared. Well, if you flip the larger and the smaller denominators here, you just rotate the ellipse slightly, okay? So your ellipse is going to be elongated along the y-axis. That's going to be the long part of the ellipse. That's the major axis. And then the minor axis will be, the narrow part of the ellipse will be along the x-axis, right? So when you're trying to figure out what an ellipse looks like, when you're looking at an equation for ellipse in standard form, what's really important is to tell which is the larger denominator, because that tells you how the ellipse is going to be positioned, or how it's going to be oriented, I should say, okay? It's always going to be positioned. We're only studying ellipses where the center is at the origin. Okay? I mean, you can shift ellipses in different locations, but we're only going to consider ellipses that are centered. By the way, we're also not going to look at ellipses that are rotated slightly. Rotated a little bit. The major axis will always be along either the x-axis or the y-axis. We're not going to ellipses that are slightly rotated just a little bit. But we have a very simplified form for ellipse, and this is already complicated enough. Now, one other important thing, okay, is where are the focal points located? Remember, the center is not the same as a focal point, all right? So here's how you find the location of the focal points. The focal points always are along the major axis. Focal points are always along the major axis. So if the major axis is along the x-axis, the focal points are going to be on the x-axis. If the major axis is along the y-axis, the focal points are going to be on the y-axis. Now, how do you find then that value where the focus is on either the x or the y-axis? you use this equation. So this equation is very simple. That kind of looks like the Pythagorean theorem, right? Okay. You know, the Pythagorean theorem says c squared equal a squared plus b squared. Okay. But this equation is just the conjugate of, this is called the conjugate of the Pythagorean theorem, where we change this plus to minus. Okay. So in this ellipse equation, you have c squared is a squared minus b squared. And you can solve this equation to find the value for c. That will tell you the location of the two focal points. Now, remember, if you take the distance from the focal points to the ellipse, so if I were to start at this focal point and walk up here to the ellipse, and then down to this focal point, that distance is always the same for an ellipse. Okay, so the radius is not always the same for an ellipse, right? If you start at the center and walk out to the ellipse, you may go different distances, correct? But what does stay steady in ellipse is this distance. If you start at one focal point, go straight to the ellipse, and then come down to the second focal point straight, that total distance is always the same. So if we started here at this focal point and walked over here and then walked back up to this focal point, that total distance would be the same as this total distance. That's what is steady in an ellipse. Okay. Oh, by the way, if you take if you're standing at this focus and you shine a light, right, a light beam at this, at the ellipse, at the edge of the ellipse, it will bounce off down to this focal point. If you're here and shine the light here, it will bounce off to this, be reflected to this focal point. That's a useful physical property of an ellipse. Okay. For instance, if you're standing in an elliptical shaped room, if you're standing at the focus and you speak, okay, guess what's going to happen? The sound waves are going to travel out to the ellipse. They're going to bounce off the ellipse and do what? They ain't going to go back here. They're going to be reflected to the other focal point. So if you're standing here and you talk, someone standing at this focal point is going to be able to hear you very clearly. Okay, right? Okay. That's just the physical property of ellipses. That's called the reflection property. That also makes ellipses useful in applications. Okay. All right. Well, so much for kind of describing ellipses in algebraic form. Let's actually apply some of that knowledge. So let's try this. So let's see if we can find the foci of this ellipse. So where are the two focal points? And see if we can sketch the graph. So we're actually going to have to find other things as well. Okay, we're going to find the focal points, but we're also going to have to find where the vertices of the ellipse are as well. Okay, we're going to figure that out. Remember, those are the endpoints of the major axis, and we'll also have to find out where the endpoints of the minor axis are as well, and then we can sketch the graph really easily. Remember, we're only dealing with ellipses that are centered at. We're only dealing with ellipses that are centered at the origin. Okay. All right. Let's before we get into this, let's stop and let's take about 10 minutes, and then we'll come back and do this one. Okay. Because this is going to take a few minutes. So let's take our break first. So for you guys at home, you can take the break. We got 10 minutes. Then we'll come back and finish and figure out what this ellipse looks like. We'll come right back to this problem and see if we can figure out all the details of this ellipse. So the first thing we want to do, remember, is in standard form, we want this number on the right hand side to be 1, not 144 or some other value. Okay, so the first thing you'll want to do is divide everything in the equation by 144. So you can make this exactly equal to 1. So let's see what happens when we do that. So I'm going to take 16. Let me lower the screen here. So I'm going to take the 16 x squared and divide that by 144. And then the 9y squared, let's also divide that by 144. And then, of course, we have 144 divided by itself, which, you know, by design is going to be 1. So we get the right-hand side looking correct, right? Now, let's simplify just a little bit on the left-hand side, because I think 16 goes into 144, right? And so you can divide 16 into 144, and you'll end up with just x squared over 9. So that's looking a lot more like that standard form for x, right? And then plus, and then 9 also goes into 144 because that's 16, correct? So we get y squared over 16 is equal to 1. So see, this looks much more like an equation for an ellipse. Now, also, let's take those denominators and write them as perfect squares. All right. So you can write 9 happens to be a perfect square. So you can write the 9 as what number squared? Yeah, so that's 3 squared plus, and then 16, of course, is 4 squared. So you can write the 16 as 4 squared. And now really you're on your way. There you have the equation for the ellipse written in standard form. Okay, now let's write down the A, B, and then we'll figure out what the C value is. The A and B are easy to determine because you'll read them from the equation, right? So what's the A value going to be for this ellipse? Actually, just the 4, right? Okay, it comes from the 4 squared. Remember, the A is going to be the larger of those 3 values, A, B, and C. All right, so A you will take to be 4. B will be 3, correct. So this tells us immediately, right? We can already, if we want to, we don't have to, but we can already start drawing in a little bit of the ellipse, right? Because the A squared was located under the y squared. That means this ellipse is elongated along the y-axis. The major axis is vertical. And the y-intercepts are going to be +4 is one of them, and -4 would be the other one. 1, 2. All right. So this is going to be major axis. So the foci will also be located along the y-axis. All right. Of course, the center is, as always, going to be there at the origin. All right, but that's kind of not really useful for ellipses. The b value tells us the x-intercepts in this case. So there's an x-intercept at +3 and another one at over here at -3. So you can already see what that ellipse is going to look like, right? Okay. So really, you can actually already draw it. Remember, this is a vertex of the ellipse. This is a vertex of the ellipse because those are the endpoints of the major axis. This does not count as a vertex. I don't know what that's called, but it's not called, well, other than x-intercept. It's not called a vertex, and this also is a vertex. All right. Now, but we do want to figure out where the foci are located, right? They're not part of the ellipse. They're not really part of the graph, but we do want to figure out where they are. And remember, that comes from the equation, that altered version of the Pythagorean theorem, right? C squared is a squared minus b squared, right? So you know c squared is going to be a squared was 16, right? And b squared was 9. So c squared is 7, which means c is the square root of 7. And 7 has 2 square roots, so I'm going to write them both. Because you get, actually c is supposed to be the positive one. So c is technically square root of 7, but you do have 2 focal points, right? One of them is at positive square root of 7 here on the y-axis, and the other one's at minus square root of 7 on the y-axis. How much is square root of 7 about? We need a decimal x, 2.7 or something like that. 2.64. Okay, 2.6. I was off. Comparison. All right, so up here at about 2.6 is one of the focal points, and then down here at minus 2.6 is the other focal point. If you wanted to write them down perfectly, you could say one focus is at square root of 7, I'm sorry, 0 and square root of 7 because it's on the y-axis, right? And the other focal point is 0 and minus the square root of 7. So on y-axis. And then just try to your best, right, to connect these points, right, these intercepts with a nice smooth elliptical curve. Not too bad. Okay. Now, there's one other measure that is important for ellipses and important for applications. It doesn't really help us too much with graphing the ellipse, but it is important in applications of ellipses, and this is called the eccentricity of the ellipse. And it's easy to compute the eccentricity of ellipse. It's just the c value divided by the a value. Okay, so whatever you calculate for c, divide that by whatever you calculate for a, and that quantity is called the eccentricity. That's always less than 1 because c has to be less than a always, right? But it also cannot be 0 because it cannot be 0. Otherwise, you will have a circle. If the c value turns out to be 0, you don't have an ellipse. You actually have a circle. So, so it's not going to be 0, and it's not going to also be ever 1. It's somewhere between 0 and 1. But as the eccentricity gets closer to 1, so if you have a large eccentricity, relatively large, because it can't be more than 1, but if it's close to 1, you have a very long, thin ellipse, okay? As the eccentricity gets close to 0, you have a more circular ellipse, okay? And in applications of ellipses, the eccentricity is useful. Again, I already mentioned one important application of ellipses is in orbits of celestial objects, right? Like, for instance, the planets around the sun. Here are the eccentricities of those elliptical orbits. Notice, as I mentioned, right, the Earth's is very small. It's just 0.017. So, as I mentioned, right, the Earth's orbit is very circular, okay? Which is why the early astronomers made a mistake and thought it was a circle, okay? Because its eccentricity is so small. Mercury has a much relatively greater eccentricity. It's 0.2. So that's quite a bit more eccentric than the Earth's. So this means Mercury's orbit is a lot more elliptical than the Earth's orbit is. For instance, Venus is almost perfectly circular. Okay, and another one that has a more elliptical shape to it is Pluto's orbit because its eccentricity is 0.248. Okay, notice there's an asterisk there now with Pluto because Pluto has run into disrepute now as a planet, so it's often categorized as a planetoid and not a genuine planet. All right, read a long article about this in the New York Times last week. Exactly what constitutes planets, what doesn't constitute planet. There are, by the way, there are many other known or suspected now planetoids. Okay, so some at great distance now from sun are suspected to exist. They're looking for them very closely. Of course, they're hard to find because they're very dim, being so far from the sun. So this is a very active, part of astronomical research, right? It's looking for things orbiting the sun. Yeah, go ahead, Emil. Vertices, yeah. All right. So now I have one for you guys to do. Okay. I broke it up into steps though, so to try to make it a little bit easier. So we'll do it one step at a time. and then we will have people share their results, right? Okay. All right, you guys at home? All right. Unfortunately, let me write the one important the one important equation there, right? But it's easy to remember. Remember this is called the conjugate of the Pythagorean theorem. When you change a middle term in an expression from minus to plus or minus, that's called the conjugate of the expression. So this equation that governs ellipse is the conjugate of the Pythagorean theorem because we have a minus here instead of a plus. All right, so I'll rewrite that for you as a reminder. All right, but let's see if we can answer some of these questions. So it tells us now the vertices of an ellipse are at these 2 points. Notice those points are on the x-axis, right? Those are points on the x-axis. Okay. And the foci are also located on the x-axis, right? At these 2 points. So there's 4 and 0 and minus 4 and 0. And then the foci are at 2 and 0 and minus 2 and 0. We want to write down what's the equation for that ellipse. Okay, so in standard form, what does the equation for that ellipse look like, right? So you're kind of given the geometric description of the ellipse, and we want to write down the algebraic description of the ellipse, which would be that equation, right? And then we want to make its graph, which is, you could already kind of make the graph, right? You could start it anyway, just from the information that you're given. But so the graphic is really the easy part. The hard part here is writing down the equation correct. So first things first there, tell me what are A and what are C for this ellipse, okay? Should be able to write that down really quickly. What is the A and what is the C, okay? I'll let y'all, yep, y'all can write that down in your paper. I don't need to go around and look at this one. So, this is pretty straightforward. So from the information that you're given, we'll just ask somebody to share with us what they got there. It's like just a few seconds. Okay, so let me ask someone. Online to share with us. What did you guys get for A, and what did you get for C? Someone at home there. You can either type that in, or you can just tell me what's the A value and what's the C value here. Something confusing about the vocabulary there? That should be pretty straightforward. Someone online? Ah, Giselle, thank you. That's right, Giselle, right? Okay. A is going to be 4. Right, because we're told where the vertices are, right? Okay, and the vertices are always remember, the vertices are the endpoints of that major axis, right? And they are associated with that value A. Yeah, I mean, in a way, yes, but normally when we're asking for what is A, we would just say the positive value, right? Okay, but once you know that, you have to know that, you're going to have your vertices at +4 and -4. All right. What's the C? So Giselle told us, right? It's 2, correct? Because C tells us the location of the foci, right? And we were already told, oh, the locations here are at 2 and -2. Great. Right. So perfect, right? We can just get that right immediately from the from the information that's given to us. Now we want to find the B. That's the one we're actually going to have to, right? Okay. So what will the B value be? So that will tell us, in this case, that would correspond to the y-intercepts, right? Because the these are the x-intercepts. Those come from A, and then the B value would tell us the y-intercepts. But what is B? Yeah, I think we have to use that formula. Okay, so plug those numbers into that formula, Emil. Yeah, so Emil says, oh, we're gonna have to use our formula, right? Okay, our elliptical formula. So see if you can use that formula and deduce their B. Take about a minute. Solve that. Okay, so someone in class here, can y'all describe the equation for me here that we're going to solve to get B? What does that equation start off like? Yeah, 2 squared equal 4 squared minus B squared, right? Okay, and now we have to solve that for B. So how do we go about solving that for B? What would y'all do here in this equation to solve for B? There are various steps you can take. You want to simplify the squares? So sure, right? Why not? Right? So you can write this as 4 and this is 16. So you get 4 is equal to 16 minus B squared. All right. Now what? You divided, or I think you mean subtract, right?
Sure.
So let's take the 16 and shift it to the left-hand side, okay? Because as Amanda says, let's get the B squared by itself. Yeah, that's one of our goals there. All right. So let's get the B squared by itself. But remember, it's minus B squared. So be careful. The minus sign stays there. And then when you shift the 16 to the left-hand side, that becomes negative 16. And then 4 minus 16 is minus 12. So you have minus 12 is equal to minus B squared. All right. So Amanda, don't divide by 16. Not divide by 16. Just want to, you can just move that 16 to the left-hand side. Okay. If it were multiplied by the B squared, then you would have 16. Yeah. Okay. Yeah. All right. Now we have minus 12 is minus B squared. I don't like those minus signs. So can I do something with those? Okay, you can just cancel them out, right? Technically, what you're doing is dividing both sides or multiplying both sides by minus 1. Okay, and you would get 12 is equal to positive B squared. And now you're in great shape, right? How do you now solve for B? Square root, right? So B is the square root of 12, right? Which, and if you want to, you can leave it as square root of 12. If you need to graph B for some reason, you would want to write down its decimal approximation, but try to avoid that until you really need to graph B. Okay, just leave it as square root of 12. What is the square root of 12? The approximate 3.46 or about 3.5. Okay, all right. So I'm going to write that down for future reference, but not going to use that yet. Let's leave B as square root of 12, because the next thing I want to do is write the equation. Now the equation just writes itself, right? Because in standard form, you have x squared over something, right? Plus y squared over something, and equal to always 1 on the right-hand side. So the right-hand side is always easy to write down. That's going to be 1. What do we put under the x squared and the y squared? Right, under x squared, we'll put the a squared, right, Emil? So that is 4 squared. Why do you know the a goes here and not here? That's right. A will go under x squared, but why, Robbie? Sometimes a goes under y squared.
I think it's.
The vertices, that's right, are where? On the what? On the x-axis, right? The vertices are on the x-axis. This ellipse is elongated along the x-axis, so it's longer horizontally than it is vertically. Okay, so that means the larger of the a and the b will go under x. All right, so you put a squared under x squared, and then the b squared goes under the y squared, and that's it. So easy, right? So you have x squared over 16 plus y squared over 12 is equal to 1. Did y'all get that? That's right. If the vertices were on the y-axis, then the a goes under y. Yeah. Okay. Let's see. We can graph this now really easily. So we know the vertices here are at 4 and minus 4, and the x-intercepts were at 3.5 and minus 3.5. And now you just have to draw your ellipse. This one is pretty circular, right? Okay. So even though that's fairly circular, the notice the eccentricity is not going to turn out to be that high. The eccentricity is c, which is 2 divided by a, which is 4. So the eccentricity is still only 0.5. I'm sorry, the eccentricity is not going to be that low, even though this is close to a circle, and visually it's close to a circle, right? The eccentricity turns out to be 0.5. Remember, the closer you get to 0, that's when you get more and more like a circle. Remember, the ellipse of the Earth was 0.017, way less than 0.5. So it's very circular, right? All right. I'm going to show you this one. Okay, so because this one has a little bit of variation. All right. So it's, I mean, but the instruction is pretty straightforward. It says find the equation of the ellipse shown here. All right. So you can see that ellipse is taller than it is wide, right? So that means that the vertices are on the y-axis. So the a value will be this y-intercept, right? And then minus a would be this second y-intercept, right? The negative y-intercept. And these are then what values? B, right? So one thing we do know immediately here is that B is equal to what? 3. But that's not a lot of information to start with, right? Okay, we just know B is equal to 3. All right. So we can see A there, but we don't know what A is equal to, and then that's going to make it hard to figure out what C is, right? Because I have no idea, right? You know, the focal points are somewhere here on the y-axis, but who knows where, right? Now, however, we do have one other piece of information that's going to be important to us. We do know one point on the ellipse, okay? So we know the point 1 and 10 square root of 3 over 3 happens to be on the ellipse, okay? So we know this kind of one kind of almost random point is on the ellipse. So how can we make use of that information to actually figure out what the equation for the ellipse is? All right, so let's write down what that equation is going to look like, though, once we're finished with it. So what will it look like? You'll have x squared over what goes under the x squared in this picture? 3 squared, right? The b value squared go under the x because it's the minor axis that's along the x-axis, right? In this picture. Plus, now we have we have y squared over a squared, but unfortunately, I don't know anything about a is equal to, but I do get a little break here. What's on the right hand side? Not a variable, just going to be always one. All right. So there's the equation that I'm trying to figure out. Okay. But sadly, I'm wondering here how to figure out the a, right? You don't have to figure out values for x and y because those are variables in the equation, right? In your final equation, x squared stays there and y squared stays there. But we do have to have this specific number for a. So we got to figure out what a exactly is. Now, here's where that point is going to help us, right? Okay. This point is on the ellipse. So that means this point must be a solution to this equation. This point has to be a solution to this equation. Otherwise, the point will not get on the ellipse. So that tells us if I plug 1 in for x, and then this weird number in for y, the equation has to be satisfied. This equation has to be true. So notice when you plug in the x coordinate and the y coordinate, you get an equation, but it only has one unknown in it, a. And now maybe I can solve this equation for a, see? Okay, and then I'll be done, right? So that substitution may allow me to figure out correct value for a. Let's see if we can solve this equation now. Well, I know the first number, that's easy, that's 1/9, right? Plus, now when you square 10 times the square root of 3, what does that give you? Well, it's going to give you 10 squared and square root of 3 squared. Both of these factors are going to get squared. But these aren't hard numbers to square at all. What's 10 squared? 100. And what's the square root of 3 squared? 3. Yeah, don't write 9, right? It's square root of 3 squared is just 3 over a squared is equal to 1. Oh, that's not too bad at all. That's 1/9 plus 300 over a squared is equal to 1. Now let's see what we can do here. Let's subtract 1/9 from both sides. So I'm going to bring the 1/9 over to the right hand side. So I get 300 over a squared is equal to 1 minus 1/9. And how much is 1 minus 1/9? 8/9, sure. That's 9/9 minus 1/9 is 8/9. Oh, this is looking now much easier. Now we get this equation. This equation now is called a proportion because you just have one fraction equal to another fraction. And proportions are really easy to solve. So whenever you have one fraction equal to another fraction, there are some tricks you can use to solve simple equations like this one, but you can go multiple routes. But one shortcut to solving an equation like this, a proportion equation, is use what's called cross multiplying. Have you ever heard that term before? That works when you have one fraction equal to another. So you multiply the numerator of one side by the denominator of the other side and set those two things equal. So let's see, what would I have here? 300 times 9, how much is that? That's 2,700, right? Is equal to 8 times a squared. Well, that's looking much better, right? So how can I get rid of the 8? Divide. I was going to ask you, Amanda, but you said it. Yeah, here you divide, right? Don't subtract. So you get that 2,700 divided by 8 is equal to a squared. Is there a 2,700 divided by 8? Oh, it doesn't come out perfect there. Oh, shoot. Okay. So let me just leave it as 2,708 for the time being. So what's a? A by itself, though. Square root of this, right? Yeah, I thought that would come out to be a nicer number. Thought this was, oh, this worked out nice. Well, there it is. Okay, so A is the square root of 2708. Okay. Of course, when you plug that now back into the equation, you're going to square it. So the square root's going to go away anyway, right? So it looks like we end up with, right up here, it looks like we end up with, for this equation, x squared over 3 squared plus y squared over 2700 over 8, right? Because that is the square root of 2700 over 8 squared is equal to 1. So if you want to, you can write this as x squared over 9 plus 8y squared over 2700 is equal to. See what I did since I was dividing by, right here, since I was dividing by, where is that? Since I was dividing by 2700 over 8, that's the same as inverting and multiplying. So that's the same as multiplying by y squared by 8 over 2700. Oh, that looks good enough there. All right, so like that. Well, I thought the arithmetic would come out cleaner, but this is still an easy equation, right? Okay, there's the equation for that. Whoops. Okay, let's finish here by letting you try one, right? And let's see if y'all can see if we can, if y'all can do this one. So it's just find the equation of the ellipse such that the endpoints of the minor axis, not the major axis, endpoints of the minor axis are at 0 and plus or minus 2. So that's on the y-axis, right? So that's the endpoints of the minor axis are on the y-axis, and the distance between the two foci is 6. The distance between the two foci is 6. Let me help you a little bit here. Let's draw a picture of this. So the endpoints of the minor axis are at 2 and minus 2, right? So the ellipse is elongated this way, right? Because this is the minor axis, and the distance between the foci is 6. So the foci aren't on the y-axis, they would be where? On the x-axis. But now where would they be located if the distance is 6? What now? Plus or minus 3, right? Because the distance has to be 6 between them. So one would be at 3 and one would be at, there you go, at minus 3. Those are the foci though, right? Those aren't the vertices of, okay? Those are the foci. So can you write down now quickly the equation for that ellipse? One of the foci there at 3, one of them at minus 3. 2 and minus 2, endpoints of the minor axis. So what's the equation for, what's the final equation for that? Okay, you guys at home too, right? See if you can write down the equation for that ellipse. Remember, these are the focal points, and those are the top and bottom of the ellipse, right? See that distance there, this focal point to this one has to be 6, right? Which it is. Our timing is perfect. Okay, guys, so what's that equation that we need to solve to finish this? What's the basic equation? Oh, well, okay, yeah, so, yeah, I am being a little bit ambiguous, right? Okay, yeah, the equation we want to create is this one, right? X squared over, and you're right, Amanda, it's gonna be a squared because the major axis is along the x-axis, right? Plus, y squared over b squared is equal to 1. But to determine the a's and the b's, right? I was talking about that equation, but so what's that? What's that? C squared equals, yeah, a squared minus b squared, right? And what do we know in this equation? Do we know a and b? A and c? C and b, yeah, right, okay. The b value is this one, right? Because that's the points of the minor axis, correct? So you can fill that in. And the C we know because that comes from the equation of foci, right? So the C is 3. So we can fill that in as well. And now we have this very easy equation to solve. 9 is equal to a squared minus 4, which I think means a squared is what, 13? So a is the square root of 13. What is the square root of 13? Approximately 0.7 or 3.6? Wow. Just right here? I always have trouble guessing the shape of these things from. I guess I haven't worked enough with the ellipses. So the vertices are really close to the foci here, right? Okay. And so you can draw the picture really easy, right? So just connecting the vertices. What the picture looks something like this. The equation is that's also easy to write down. So we have x squared over, yeah, square root of 13 squared, which is 13, right? Plus y squared over 2 squared, right, is equal to 1. So you end up with x squared over 13 plus y squared over 4 is equal to 1, or that picture. Just seems to me, well, yeah. Between C and A, well, you know that C is always less than. The focal points are always inside of the vertices. Okay, so no, C is always less than. Yeah, the part, yeah, you maybe did miss part of the question. It told us about the, didn't tell us where the foci are, but it told us about the foci. It said their distance is 6. So we deduced then that they had to be 3 and minus 3. That gives it a distance of 6, right? Okay, yeah. Okay, all right. Well, that's all the examples I have for ellipse. There is a separate ellipse homework that's not in the 1.9 homework, but I haven't posted that yet. Okay, so I'll get around and posted that. But remember, you're working on the 1.9 homework. Okay, when we come back on Wednesday, then we're finally going to talk about lines. So in a way, that seems like it will be easier, but we're going to go into it in much more depth. So in a way, it will be harder. First, we'll have a little recall though. Y'all can cheat if you want to. After I post these notes. Oh, there's the recall for next time. So that's what we'll start with. All right. It'll be in the notes, the ellipse notes that I post today. Okay. So I'm getting ready to stop the tape. Stop the tape. So you got a homework due tonight, right? Okay. So don't forget about that. Done with it. Yeah, that's a great feeling. Okay. So you can work on 1.9. See y'all Wednesday.